are going to start our unit 3. And last unit we did some factoring with quadratics. This unit we're going to start graphing them. And actually that's how we're going to spend a lot of our time for the remainder of the trimester. We'll be graphing quadratics. Like, oh wait, Miss Guy, quadratic. You were using that word quite a bit last unit, but I'm still kind of fuzzy on what it means. Quadratic means your highest exponent is a 2. So my highest exponent being 2, we take a look at the very first example, y equals x squared. That's our parent function. We talked about parent functions with our exponentials. That means the parent function is as basic as you can get. So for a quadratic, the most basic we can get is y equals x squared. Quadratic means highest exponent on your variable is a 2. Always. If it's higher than a 2, our graph will not be a quadratic. It will not look how we're going to graph our ones today. So to keep this simple, I know I had you guys grab graphing calculators, but we're going to graph this first one. Since it is very basic, we're going to go ahead and fill out the table ourselves. So when we create a table to make our graph, we just substitute values in for x to get values out for y. So if my x value is -2, I put -2 in for x, and I squared in this case. Now, with negatives, we talked about those negative bases when we did our exponent unit, our exponential unit. You have to make sure in your calculators that you always put parentheses around the negatives when you substitute in. Otherwise, your calculator will read it as, if you don't put the parentheses, your calculator will read that as square the 2 and then make it negative. So if you don't put parentheses around it and you just put -2 squared in your calculator will tell you it's -4 because it squares the 2 and then it makes it its opposite. So this should be +4. If I put -1 in and square it, +1. 0 squared is 0. Good general rule of thumb, whenever you substitute in, be it positive, be it negative, put parentheses around whatever you substituted in. And then we get our 2 squared. It's once again +4. Do you guys notice anything about that table? What do you notice about those y values? If we were to fold the table in half at 0, what would you notice if we folded it? They're the same, right? Does anybody know what that's called if I fold something in half and the two sides match perfect? Anybody remember what that's called? Maybe from an art class if you took art? Yeah, symmetry. They're symmetric. So if our table of values is symmetric, our graph probably should be too. So let's go ahead and graph those ordered pairs. We have -2, 1, 2, 3, 4. Make that a little bigger for you guys. There we go. And then we have -1, 1, 0, 0, 1, 1, and 2, 4. So our graph, in fact, it does turn out to be symmetric. Now this graph, I know some of you have graphed absolute value before, some of you have not. This graph, it has that kind of similarity to that absolute value graph where it's symmetric. If you graph absolute value, you get a V shape where both sides are a straight line. This, when you graph a quadratic, the shape you get is called a parabola, and it's kind of a U shape. It's more curvy than straight. So the name of our graph you get is called a parabola. Looks like parabola. The shape graph we get whenever we graph a quadratic is a parabola. So anytime you graph an equation where the highest exponent for your variable, in most cases it's x, is a 2, you're going to get that U-shaped graph. It should be symmetric, and it should be that curvy looking U shape. So what I want to do to start today is just introduce you to some of the features of this graph, and then we're going to spend some time graphing a few and getting used to those transformations of the graph. So just a few things about this graph. The first part of this graph that we're always going to pick out to graph is called the vertex. The vertex is the point. Go ahead and label it on here. And there's a few different ways people like to phrase this. The vertex, and we will be reflecting this graph, so sometimes it'll open up, sometimes it'll open down. Some people like to see the vertex that it's the lowest or highest point on the graph. You could also say the minimum or maximum point, up to you. Some people view it as, I like seeing it as the highest or lowest point of the graph, or that minimum maximum value. Some people view it as, they like to say, Miss Golly, it's the middle. It's the middle of the graph. And it is. It's that point where if we fold it in half, the two sides match. Some people see it as the middle. So kind of figure out for yourself. That's going to be a very important point for us. So kind of figure out for yourself which one makes most sense in your brain for that. So that vertex point, that's going to be, depending upon how the graph opens, we'll see it reflect today also, which means it's going to open down. You might view it as the low or high, the min or max, or you might see it as, yeah, that middle point thing you're saying makes the most sense. So kind of however you want to view that. Another feature of this graph, and we haven't drawn it in yet, it's called the axis of symmetry. It's going to be, I'm going to go ahead and label it on the graph. It's kind of hard to label on this one because it literally goes right down the y-axis for this one. This is your axis of symmetry. And it's always going to be a vertical line. It's the vertical line that if you fold your graph in half on it, the two sides will match up perfect. So the axis of symmetry, it always splits our graph in half. It's always a vertical line. So vertical lines, we haven't reviewed graphing those in a while. Vertical lines always have x equals. We reviewed a horizontal line last class and it was y equals. So a horizontal line is always x equals. In this case, it's x equals 0, but we will move our graph around today and we will see that number change. So for the axis of symmetry, it's always going to be a horizontal line through the vertex. If you want to add some little side notes in there that it cuts the graph in half, or it's the line, if you fold on it, the two sides will match up. Since it's a horizontal line, I'm just going to put a little note here. It's always going to be x equals some number, and we'll talk about how we find that number as we graph a few more of those today. So those two features, those are going to be pretty important for us as we graph, especially that vertex point, super important. The axis of symmetry is going to make our graphing a little easier as well, a little bit quicker for us. Now, the concave up or down piece, that's just how our graph opens. If it's concave up, I'm just going to draw a little picture for each one. Concave up, the graph opens up and it looks like a U shape. It's the way the graph opens. Don't let the word concave throw you off. It's just describing that it's kind of that U shape. And then concave down is when we reflect it and we flip upside down. And we're going to see today how we can tell from our equation which way our graph should look before we graph. It's going to be one of the things we talk about before we even graph. Domain and range, we talked about those a lot with our exponentials. The domain, we recall, are all possible inputs. And in most cases, that means our x values. We talked about that, the exponentials. I don't always just want to call them x values because some equations aren't written with x's and y's. Some use variables that are more fitting to the problem situation. So you might not have x's and y's. You could have f's and g's. You could have r's and s's. You could have a's and b's. You might not always have an x there. So I want to be careful with saying that's always an x. Now, when you go to square something, and we just saw it in our table, I can square a positive number. I can square a negative number. I can square 0. Can I square fractions and decimals? Is that okay? Could I do that? Could I square a half if I wanted to? What do you guys think? Yeah, we could square a half if we wanted to. We could square 1/3. We could square any decimals we want to. So the domain for our quadratics, it's just like our exponentials. We're always going to have all real numbers. And you can put that R symbol that we used, if you would like, kind of that, I call it a double-legged R. Some of you said it looked kind of like a T next to an R. Yeah, kind of depends how you draw it, yeah. So just like our exponentials, we can put whatever we want in for x. The range, just like our exponentials, is where we have to focus in. So the range is all possible outputs. And in this case, it's our y values. But again, I don't always want to say y values because, again, you could have really any variety of variables you want, especially if you do application situations. They're not always x and y. So with those y values, it's going to be like our exponentials. If we look, and I will scroll back down, Miss Golly, I'm still writing. If we look even just at our basic parent function, our y equals x squared that we graphed, every input that we put in, every x value we put in, the result came out to be positive or 0. So we can't get a negative result in this case. So if I look particular at this graph, all of my y values are going to be above or equal to 0. So very similar to what we do with our exponentials. The only add-in though, remember with our exponentials we had that imaginary line we couldn't touch or cross, we couldn't ever reach it. Now in this case though, our y value for this one can actually be 0. So when we do our range for our quadratics, we're going to have that equal to there with our y. But it's going to be the same idea as our exponentials. We figured out where our lowest point, or sometimes our highest point was, and then decide if your graph is above or below. So with your range, you're either going to have y is greater than or equal to, or y is less than or equal to, and then we have to fill in the appropriate number. And we'll talk about that today. We're going to do several graphs together today. Yeah.
What's that third word in range?
Outputs. Outputs. There we go. So all possible outputs. Couple other features on our graph, and we're going to get more specific on these last two features in a couple lessons from now, or actually our next lesson we will. We're not going to focus so much on them today, but I want to introduce you to all the key parts today, and then we're going to build from there throughout the week. So our x-intercepts, oftentimes referred to as the zeros, we refreshed on x-intercepts and actually y-intercepts on one of our review questions last week. The x-intercepts is where the graph crosses the x-axis. When you graph a quadratic, they're oftentimes referred to as the zeros, so I will use that interchangeably. So it's where the graph crosses the x-axis, and again, we kind of refreshed on finding that x-intercept last week with standard form of a linear equation, and that's where we put 0 in for y and solve for x. So our x-intercepts are always going to be a 0 in for the y value. So the idea of x-intercepts, when you guys graphed your linear equations in standard form during first trimester, you guys found x-intercepts, and to find that you put a 0 in for the y and you found your x. You might not have actually put the 0 in, you might have just covered it up, but that's the same idea. So then the y-intercept, kind of same definition, but interchange x and y. So it's where our graph crosses the y-axis. Where graph crosses the y-axis. Put 0 in for x and solve for y. So for a y-intercept, that x-coordinate will always be 0. So whichever intercept you're trying to find, the other variable is 0. Whatever intercept you're trying to find, the name of it tells you what axis it should be on. So if I'm finding the x-intercept, it's going to be on the x-axis. To find the x-intercept, I put the 0 in for y. So the name of it can tell you a lot about where it is on the graph and how you can actually find it. So what we have on this first page, guys, we have our parent function for our quadratic, that basic parabola shape. And then we've talked about a lot of the key features we're going to find. The only two we're not really going to focus on today are the bottom two. The x and y intercepts, we're going to get to that. If we do all this information one day, I think it's going to be just too much. I want to build into it. So today we're going to focus on our vertex, our axis of symmetry, determining if we open up or down, and the domain and range. We're also going to throw the transformations in there too. Okay. So this front page can kind of be our reference. If you're ever asked to find a part of the graph, you're like, oh shoot, I'm not quite sure what that word means yet. Flip to the front page of this note sheet, and that definition should be there for you, or even labeled on your graph. Okay. So if you go to the back side of the first sheet, we're going to start playing around with that parent function. And to do that, we're going to use our graphing calculators just like we did with our exponentials. Whoa, hang on. Maybe that'll shift back up there for me. That's really strange. Wow, that's interesting. I don't know why that shifted down there. Okay, so I'm just going to delete my ink out of here. Okay, oops, that made that disappear too. Okay, so I'm going to go ahead and sketch my graph back up here. You guys already have it on your sheet. And now it reappears again. Sorry guys, I'm not sure why that's doing that. Let's delete it. Maybe that'll make it. Okay, there we go. All right, so what we're going to do, the parent function I have on your graph for you. And now we're just going to see, for example, in the first one, adding a 3 onto that x squared. How's that going to change my graph? And then we're going to pick out all of our pieces that go with it, okay? So let me grab my graphing calculator here real quick. Maybe. There we go. So if you want to, you can go ahead. You are going to go to the same spot we did for our exponentials. We're going to go to our y equals. And make sure everything's cleared out in there. So that y equals is in that very top left, right underneath our viewing window. There we go. And we're going to see what adding 3 does. So go to your y equals and clear out what's ever in there. I know we use these last with our exponentials and things. If you guys have any plots that are highlighted, see how mine's highlighted up at the top? Arrow up and put your cursor on any of the plots that are highlighted and press enter. So your screen should look like mine. Because sometimes if those plots are highlighted, there's some misinformation in there and you get a graphing error, and we don't need the plots on. All right, so we want x squared plus 3. The x key is the same one we use for our exponentials. It's the one right next to the alpha key, highlighted in red on my screen. It has the x, capital T, a little, looks like a O with a line through it. It's a little sigma and then little n. The squared key, guys, this one we don't have to use the caret key we were using with exponentials. There is actually a squared key in the left column, highlighted in red on my screen right now. So it's below your second key. It's 4 down. It is an actual x squared key. The catch with that one is, though, it just gives you the exponent. It doesn't give you the x also. So you have to type the x, and then you have to go to the squared key. All right, and then we need +3. And we just need a +3. So let's go ahead and let's check our window real quick. Go to your viewing window. And mine is like crazy all over the place. So I'm going to fix mine. Remember, a nice window to start with. X is -10. Let's go X max at 10. Y min, -10. Make sure when you type negative, guys, you're using the negative key next to the enter button with the parentheses around it. Y max is at 10. And everything else, it doesn't really matter. You have that X res and the little delta X. Don't worry about any of those things. We're not concerning ourselves with those. We don't need them. All right, then we're going to go ahead and press graph. We should be good as long as our window is good. All right, so what happened to our graph? Where'd it go?
Wow.
Yeah, it went up 3, right? Does that seem kind of familiar from our exponentials we did? When we added on to the end of our exponential, it made our exponential graph go up 3 as well. So give the transformation as letter A, and we went up 3. Now, I want to go ahead and graph this. So we are actually going to skip down to letter F. I know it's not the right order, but to make our little table, it fit a little better to put it at the bottom. So we are going to make a table of values. I'm going to switch my color so it stands out. We are going to make a table of values to get a nice graph. And we're going to use our table feature from our calculator to do that. So just like we did with our exponentials. So let's go back to our calculators. Go second graph. And we know, guys, the middle of our graph is still along that y-axis. We saw it on our graph. So I'm going to go ahead and arrow up. And you should be able to find on your graph a place where you can see the symmetry. So if you notice up on mine, if you're not quite there on yours yet, notice I have the point 0, 3. Then on either side of 3, the y values are both 4s. And then if I go to the other side of the 4s, I have 7s. If I arrow up a little more, now I've got 12s. So if we fold this table in half at 0, 3, the two sides of the table would match up perfect. So if you find that place on your table, you have found your vertex. So 0, 3 is going to be my vertex. And then we've got -1, 4. Actually, I'm going to go ahead. I'm going to freeze my calculator up there so I can write those. So I'm just going to make on my table. The middle is 0, 3. And then we've got -1, 4. And I'm just going to put 1, 4. We're just going to do a few points to get us our graph. So I just grabbed a few of those points. I put the vertex at the middle, and then I picked a point on either side so we can get a nice idea of what our graph looks like. So 0, 3, 1, 2, 3, and then 1, 4, and -1, 4. And then we just draw that nice curvy U shape. So our graph has been shifted up. Our vertex, in this case, it's our lowest point. So again, if you see it as the middle point, that's okay, is at the point 0, 3. The axis of symmetry, it's a vertical line. I know these are hard to kind of see and draw in, but if we fold our graph in half along that axis of symmetry, the two sides will match up perfect. That's a nice key when you're graphing these yourself, making sure you have that symmetry. Now the axis of symmetry, it's a vertical line, so it's always x equals. And it's always what the x equals of your vertex. So all along that vertical line, any ordered pair I pick, the x is going to be 0. The x is going to be 0. We open up. Our graph opens up. And then the last piece we want to pick out are our domain and range. The domain, all real numbers, we can put anything we want in and square it. I can square positives, I can square negatives, I can square 0, I can square fractions and decimals. There's not a single number out there I can't square. Now the range though, if I look at my graph, what's in this case, my vertex is my lowest point. What's my lowest y value? How low can we go for y? The lowest y value is at 3, right? The lowest y value is at 3 at my vertex. There aren't any y values that are going to be lower than 3. And then since my graph opens up, we're going to be greater than, but can also this time equal the 3. I know a lot of you with the exponentials did a really nice job with your range. Now again, that small differences, we can equal that lower number. We will actually hit that 3. It's at our vertex point. So those are all of our pieces. As we're going through, guys, start to notice though some of the patterns when we summarize at the end. Start noticing some of the patterns, like we went up 3. Notice how there's a 3 in my vertex. X equals 0. Notice how there's a 0 in my vertex. My range has a 3 in it. So notice as we go through how some of these numbers are repeated as we find those special parts of our graph. We're going to keep them pretty simple, our equations today, and then we'll put more of the transformations together tomorrow. So today looking at simple ones and trying to pick out how noticing these patterns can make our life much easier when graphing these. So adding 3 at the end, after the squared, made our graph go up. Let's see what happens if we add the 3 as part of our term that's being squared. Let's see what happens there. All right, so let's go back to our calculator. Let's go to our y equals. I'm going to go ahead and just clear out what's there. I like to start from scratch. And I'm going to enter in just what I see. Parenthesis, x plus 3. Close your parenthesis. And then again, guys, start getting in the habit. Use that squared key. It's in the same row as your parentheses there. The parentheses are up above the 8 and 9. We use them a little bit with exponentials. So notice I entered in exactly what you see for example 2. And then let's go ahead and graph. Let's see what happened. So adding 3 inside those parentheses, making the 3 part of our square, made our graph go which way? It went to the left. Just like the plus 3 did as part of our exponent in our exponentials. So let's grab some values. Now, since we went left 3, the middle of my graph is going to be over at -3. So those transformations are going to help you know where your graph is located. My graph went to the left 3, so I need to find -3 in my table. And again, I'm just going to grab a few points. So I'm going to go ahead to the table part. I'm going to go ahead and do letter F. And I'm just going to use 3 points. So -3 zeros at the middle. That's my vertex. We can see from our table. That's where we would fold our graph in half. Would be at that -3, 0. So the transformation letter A, we said it would go to the left 3. So -4, 1, 2, 3, 4, 1, -3, 0, -2, 1. So same shape, just move to the left 3 spaces. So since we moved to the left 3, we found the vertex at -3, 0. Again, start noticing some of those patterns. Left 3, look what it did to my vertex. Left 3, that's -3 for the x. Axis of symmetry, remember guys, that splits our graph in half. This one we can actually draw in, it's not on the y-axis. If I fold my graph in half along that axis, the 2 sides should match up quite nicely for us. The axis of symmetry is always an x equals since it's a vertical line. And on that line, every ordered pair I could possibly graph, the x is -3. Again, notice that connection between the vertex and the axis of symmetry. As we go through these today, start to notice where those numbers are falling, some of those similarities. Our graph is still opening up. You want to circle it, if you want to write it, it's up to you. The domain, again guys, for all of these, just like with the exponentials, I can square any value I want. There's not going to be any value I cannot square. The range is going to take our focus. So for our range, we have to see in this case what our lowest y value is. So we have to be careful. -3 is not a y value. My lowest y value, is 0. My graph opens up, so every other part of my graph is greater than, but can also be equal to that 0. Notice again that 0 value, that range value, is part of my vertex. So notice my axis of symmetry value, part of my vertex. My range value, part of my vertex. Notice those patterns. Notice those patterns. All right, so adding 3 after our squared term caused us to go up. Adding 3 as part of our squared term caused us to go left. Let's see what happens now, our third one. We're going to just have a negative in front of our x squared. Does anybody remember what the negative did with our exponentials? What did it make our graph do? Anybody remember? If not, let's try it out. Let's go to our y equals. Let's clear it out. Now, so I don't get tons of error messages on our calculator, we do have to make sure we use our negative key. Down by the enter button, has parentheses around it. And then we just want x squared. Again, use the negative, not the subtraction. The calculator reads them very different. We learned that with our exponentials. And that's all we want. Again, we're going to keep them simple today. Let's go ahead and graph. So if you kind of thought in your brain what you kind of remembered from the exponentials. There we go. Going to go ahead and graph. That negative sign causes our graph to reflect, just like with our exponentials. So it takes it from right side up to upside down. Now, the vertex didn't move anywhere this time, so if we go to our table, the middle of our graph should be the same as our parent function at 0, 0. We didn't move up, down, left, or right, so that vertex should be at 0, 0. So we have 0, 0. At the middle, and then we had -1, 1, and +1. -1, -1, +1, -1. Transformation. Since it goes from right side up to upside down, we call that a vertical reflection. There are such things as horizontal reflections. We just don't get to them in this course. When you guys get to Algebra 2, they start adding in some of the more horizontal pieces, but we focus on the vertical in Algebra 1. All right, so we have vertical reflection. The vertex point didn't move. It's stuck at 0, 0. And if you want to sketch your graph, I know a lot of you already did. There's our graph. Axis of symmetry goes right down the middle. I know it's hard to draw when it's right on the y-axis. Axis of symmetry. Don't get lazy on this on me, guys. I will be picky on this come like quiz test time. you have to have the x equals there. If you don't have the x equals, you don't have a line. If all I write is 0 for the axis of symmetry, that's just a number. That's not even a point. It's not a line. It's just a number. Now in this case, we finally get concave down. So when you have that negative in front of your squared term, that's when our graph's going to open down. That's when our graph's going to open down. For our domain, always, always, all reals. I can square anything I want to. The range, always y. The value for it, we've been noticing a pattern. It comes from our vertex. Or you can look at your graph as well. The lowest, in this case, the highest y value is 0. Everything else, though, is either below or equal to that 0. So depending upon which way your graph opens, just like we saw with the exponentials, depending upon which way your graph is going to depend if you're greater than or less than. Okay? So what we've seen our graph do so far is go up, we've gone left, and we've reflected. There's just a couple more transformations left if we remember from our exponentials. And these two should go pretty quick for us. We're going to see what happens when we have a value larger than 1 in front of our squared term. And we're going to see what happens when we have a value smaller than 1, but bigger than 0 in front of our squared term. So let's go to our calculator. Thank you. And we'll go to our y equals. And what you can do on this one, guys, put your cursor right on that negative sign and just type a 2 on it. If you start it all back over, that's okay. 2x squared. No big deal. I'm hoping as we're going through that you guys are recognizing some of the similarities in these transformations from what we did with exponentials. When we have a number bigger than 1, and actually for this one, guys, I'm going to go ahead and I'm going to put our x squared graph on there. You don't have to, but I'm going to put our original one on there so we can really see what that 2 does. So here is our, there we go. The red one is our original parent function. Red is the original, just plain old x squared. Now, when I put the 2 in front, though, just like we saw with our exponentials, if I'm multiplying by a number bigger than 1, that makes my graph go up faster. If I multiply by 2, that means I'm doubling all the original values for my parent function. So notice the graph didn't move up, down, left, or right, but it did get more narrow. It looks like it got skinnier. The graph got stretched. The graph was vertically stretched. It went up faster. So I'm going to grab some table values here. I'm going to go to my table. My middle should still be at 0, 0. It didn't move anywhere. And it looks like we have negative 1, 2, and 1, 2 we'll use. All right. 0, 0, negative 1, 2, and 1, 2. All right, so I'm going to go ahead and graph those. And we notice our graph vertex didn't move, but it did get a little skinnier on us, so we had a vertical stretch. Remember, there are horizontal versions of these things. That's why I have to be specific with the vertical. We just don't do them in here. All right, the vertex didn't move. We're still at 0, 0, which also means our axis of symmetry didn't move either, so we're still at x equals 0. Our graph didn't flip, so we're in up. Domain, all real, always, always on these. For the range, my lowest, in this case, my lowest possible y value is at 0. Everything else, every other part of my graph is up above that 0, but it can also equal it. That's different for us from our exponentials. So if we're multiplying by a number bigger than 1 in front of our squared term, it causes our graph to stretch, to go up faster. It's going to look skinnier on your graph, is what it's going to look like. All right, our last one today Our last one today, example number 5. Now we're going to multiply by a number. It's positive, but it's smaller than 1. So on our calculator, we'll go to y equals. Now to enter your fraction in, guys, I would, for most of you, I know it's going to be easier to just do parentheses, 1 divided by 2, then x squared. If you want to, I know some of you were using the fraction feature with the exponentials. If you have one of the newer 84s, if you press alpha y equals, you get that fraction menu option. If you have the 83s, that is not there. So if you have a newer 84 and you want that, press alpha y equals and you are in business there. Okay. So we've got now a number again. It's positive, but it's smaller than 1. So now our graph, the red is our original parent function, and the blue is our 1/2. So notice when I multiply by a number smaller than 1, our graph goes up more slowly, so it looks wider. When we have that wider graph that goes up more slowly, it's what we call a vertical. This is where we use compression. And I know some of you, based on your exponentials test, some of you did like the word shrink, and that's fine. Whatever you like. All right, let's grab some ordered pairs real quick. Now notice on this one, we start to get some decimals in there. If you don't want to have to graph things like a half, that's okay in this case. Let's grab -2, 2. And 2, 2 as our other values. We don't necessarily have to graph the decimal ones if we can find some whole numbers. Okay. So we've got -2, 2, 0, 0, and 2, 2. Still that curvy shape. As best as you can, it's not that V shape. Our vertex, again, didn't move. Axis of symmetry didn't move. Still opening up. Still all reals for the domain. And our range, because we haven't moved anywhere, is still greater than or equal to 0. So the only things that cause our vertex, axis of symmetry, and range to change are if we're moving that left and right piece. Or up and down. So we have to move our graph for those to change, okay? Now, what I want to do is tomorrow we're going to do our practice. So to start class tomorrow, I want to do our summary that's at the bottom of this last sheet. So make sure you bring this back with you tomorrow. We will summarize all this and get you time to practice.
Can you move that out?